The topic of my poster is Microalgae, a sustainable fish meal alternative in aquaculture. And we are excited to share a scientific and sustainable solution to one of the most pressing challenges in the global aquaculture industry. As we know, fish meal is a vital nutritional component in aquaculture, essential for fish growth. This market is expanding rapidly. If you look at our the first graph, that shows that the global fish meal market was valued at 10.64 billion US dollar with a compound annual growth rate of 7.16%. It is projected to reach nearly 19.70 billion dollars in 2034. However, there is a major bottleneck. The traditional fish meal relies on wild-caught marine fish, meaning its supply is limited, costs are rising, and it is causing severe overfishing. The most sustainable solutions to this crisis is the use of microalgae. The question arises that why microalgae? Basically, microalgae are the foundational natural feed source in aquatic ecosystem. Looking at their nutritional profile section, and you see there are an absolute powerhouse comprising approximately 65% protein, 18% carbohydrate, and 7% lipids, 6% minerals, and 4% moistures. Research has conclusively shown that we can successfully replace traditional fish meal with microalgae in the diets of various aquaculture species. For instance, we can achieve up to 100% replacement in carp diets, 95% of the shrimp and catfish, 64.1% for tilapia, 25.6% for marine fish, and 18.6% for salmon and trout, all while maintaining or even improving growth performance. Now, let's move towards the methodology that this process perfectly illustrates the concept of a circular bioeconomy. We do not waste fresh water to cultivate the alga. Instead, we utilize aquaculture wastewater for microalgae cultivation. The microalgae absorb the nitrogen and excess nutrient from this wastewater, naturally purifying it, and the microalgae absorb the nitrogen and excess nutrient from the wastewater, that naturally purifying it. This clean water is then recycled for the reuse of water in fish rearing. Meanwhile, the cultivated alga is harvested and dried. Once dried, we have two distinct pathways. We can process the whole alga directly into the fish feed production, or we can perform lipid extraction for biodiesel production and use the remaining residual biomass as fish feed, like the zero waste and maximum utility. Like you can see that like any novel's approach scaling this up present certain challenges which we address through the specific biotechnological solutions. That let's move towards that challenges and biotechnological solution. The first challenge is low digestibility. The rapid cell walls of microalgae are difficult for fish to digest. We solve this by applying cell disruption technologies and enzyme hydrolysis of cell walls. These techniques physically or chemically break down the cell walls, ensuring the nutrients become highly bioavailable to the fish. The second major hurdles involve high production costs and harvesting difficulty associated with traditional open pond system. Our biotechnological workaround is utilizing heterotrophic cultivations alongside fermentation processing. By growing the algae is controlled, dark bioreactors and feed them organic carbon. We achieve rapid, high density growth. This makes harvesting significantly easier and drastically reduces overall production costs. And the final hurdle is the market acceptance. However, the confidence is rapidly growing as the major regulatory bodies like the FDA, the European Food Safety Authority, like EFSA and food standard have recognized and approved microalgae for commercial use. To conclude, integrating the microalgae into aquaculture not only reduces the immense pressure on marine fisheries but also establishes sustainable aquafeed production. It provides improved fish growth and immunity, supports bioeconomy and circular biotech, and ultimately guarantees lower feed costs for farmers. Thank you.